Now, so far, whatever we have seen is for long channel regime. Long channel means the channel length is going to be very, very large. When the space or when the device size is going to be a constraint, I cannot have device which is going to have a longer channel. So I'll go for short channel regime. Okay, I'll go for short channel regime. So in short channel regime, we are going to see what are the conditions in which the device can be called as a short channel device. So you know that as Moore's law states, all devices size will be keeping on reducing once in 18 months. So same way, because of continuous applications in high frequencies, the device size is becoming very, very small. And when the device size becomes very, very small, you cannot apply so much voltage across the device. So electric field, high electric field cannot be applied across a very, very small channel device. So electric field will impact the velocity. The velocity will impact the movement of charges. So everything will be impacted because of having a short channel. Because of scattering effect at smaller channels, the carrier velocities will eventually cease to increase with electric field. Even though when you are going to apply a large electric field across a small short channel device, actually the velocity should increase. When you give more voltage, the electron should be moving very fast. But because of scattering at in the short channel device, that velocity is not increasing, but it is decreasing. So as the electric field approaches 10 power 6 volts per meter, the electron drift to the velocity displays a weak dependence and saturates. So how much ever you increase beyond 10 power 6 volt per meter, the velocity will not move beyond 10 power 5 meters per second. It is going to stop at 10 power 5 meters per second because of the short channel regime. In short channel regime, scattering happens. Scattering will stop the velocity to increase with increase in electric field. Rather, the velocity will saturate or it will start decreasing. So here an example we have seen. So till 10 power 6, it will increase till 10 power 5 meters per second. So any electric field value more than 10 power 6 volts per meter, the velocity will remain at 10 power 5 meters per second. Okay. So in deriving the long channel devices, saturation drain current was assumed to be equal to the value of current at the corresponding pinch off. But in short channel, what we do, the current saturates when the carrier velocity does. So in short channel, we told that the velocity cannot increase beyond a particular point, right? So that is where you call it as saturation. So when the carrier velocity is going to saturate, we assume the current is also going to saturate. That is the condition for saturation. Whereas in long channel, you have a separate region called pentode region or saturation region where we have seen the drain current is proportional to square of VGS. But here in short channel regime, when the velocity is going to saturate, the current is assumed to saturate. Okay, the current is assumed to saturate. That is one difference we have to understand in short channel regime, and the equations will also vary slightly for short channel regime. So the drain current, we are going to use the same long channel equation only, and then we are going to modify that for short channel. So the drain current equation is given mu n cox by 2 w by l vgs minus vt into vd sat comma l. And you know vd sat by l is going to be electric field. Voltage by length is going to be electric field. So I'm going to replace vd sat divided by l. I'm going to replace by e sat. Other terms are going to be same. Okay.